So when we get out our scatter plot, what we want to be able to do is describe strength and direction. Once we realize it's linear, we want to focus on those two characteristics. Now, direction should be kind of obvious from the scatter plot, positive versus negative, but strength can be a little bit more difficult. If we're focusing on that wording of strong, moderate, or weak, what we want to understand is where's the cutoff point for when it changes from strong to moderate or moderate to weak. So with that, this is where we use correlation. So correlation describes the relationship between the two variables, describes how they're associated. For symbol, we use lowercase r. You'll even sometimes see capital R. They're the same thing. There's no difference between little r and capital R. Both of those represent linear correlation coefficient, and specifically a sample linear correlation coefficient. If we had population data, so if we were looking for this population linear correlation coefficient, the symbol that we use is the symbol rho, which is a Greek symbol, and it looks kind of like a curvy P, like this. That is rho. So that would be our symbol if we used population data, which we just won't have. We'll be using R pretty much the whole time, but that would be the symbol if it was population data. All right, below here is the formula for how we calculate our sample linear correlation coefficient. And that is a beast of a formula. We know all of these pieces. There's our X values, our Y values, the mean of the X values, the mean of the Y values, sample size, standard deviation. However, it's a lot of work to get a single number out. So what we're going to do in this section is, that's the formula, you've seen it, and I'm not going to ask you to use it. So, where that formula exists, don't worry about calculating it. Instead, what we'll do is focus more on, if you're given R, how would you translate it? Or given a scatter plot, what's a likely value for R? But you won't have to find it directly. Now, some characteristics of R. R is stuck between -1 and +1. And you'll see down here I started a number line. In fact, there's arrows on the end there, but let's actually end those arrows because it's strictly between -1 and +1, and then it can't go beyond those two values. R has no units. I kind of think of it as just, it's an index number. It's going to tell you where you land on this number line, and based on where you land, that will give you information based on positive, negative, strong, moderate, or weak. Now, the closer R is to -1 and +1, the stronger the association is. So the strongest graphs are going to be out at the edges of this. So when we get out to close to -1, that will have strong strength to it, and also at +1. Then what'll happen is as we get closer and closer to 0 from either side, the graph gets weaker and weaker. Then the sign of R is the direction of the association. So what that means is, for direction, what we'll have is anything -1 to 0, that will have a negative direction to it. So all of those graphs will have decreasing trends, and then 0 to +1 is all positive direction. So that'll have all increasing trends. And then at exactly 0, there's neither. So when you get out your value for R, the symbol that you're using, or the sign that you're using for R, is the direction. If R is positive, then there's a positive direction. If R is negative, then it's a negative direction. So that'll give us part of our description. And then our next part is describing the strength. So let's get some key values to kind of cut up our number line here. Let's grab a half, so +1/2 and -1/2. And then let's also have a cutoff at 0.8, +0.8, -0.8. These will be the cutoffs that we use. Different textbooks use different values for how to separate the strength. Anything between negative 0.5 and positive 0.5, that's going to be where we have weak strength to our graphs. Then anything between 0.5 and 0.8 on the positive side or the negative side, that's going to be called moderate. And then anything from 0.8 to 1 on the positive side or the negative side will be considered strong. So what this looks like visually, let's say we were at negative 1. Let's say R came out to be exactly negative 1. Well, at negative 1, that would be a perfectly linear relationship. So that scatter plot would actually look exactly like a line that has a negative slope to it. So our dots would completely line up into a straight negative line. Then as we go between negative 1 and negative 0.8, it'll be a very strong relationship, but maybe a little more scattered to it than we see at negative 1, but still very linear and decreasing. And then with moderate, it'll be decreasing, but then have even kind of more scatter to it, but it should still be clearly linear. And then when we get between negative 0.5 and 0, it'll be overall decreasing, but it'll have a lot of scatter to it. And then when we get to 0, that's where we have the blob of just dots kind of everywhere. Then when we get to the right-hand side, that's where our positive trend is. So let's actually jump out to R equals positive 1. So that would be the same scenario that we're seeing with negative 1, except now we'd have a positive slope. So our dots would line up completely perfectly in a line with an increasing trend. Then 0.8 to positive 1 will have a little more scatter to it, but very strong line should be appearing of the data. And then moderate would bring through a little more scatter to it, but should still be clearly pretty linear. And then when we get to weak, it'll be kind of all over the place, but still overall increasing trend. So how this is going to work is we'll have some value for correlation. So let's say, for example, I found the correlation for my data and R came out to be a let's go with negative 0.7235, something like that. So having this value for R, what it does is it tells me where I'm landing on this number line. So what I'd want to do is visualize this whole number line, see where I'm landing, which negative 0.7 is about right here on the left-hand side between that negative 0.5 and negative 0.8. So what this would tell me is that if I was describing my data, the association is in a negative direction, has a negative direction, and for strength, we have a moderate strength. So this picture here will be really helpful for evaluating what R is telling us, because wherever you're landing, you're getting two pieces of information here, strength and direction. And it just matters where on that number line are you landing. So with that, that's how we'll evaluate our correlation, is we'll get out a value for R, see where we land on this number line, and then from there we can make a sentence describing the association between the two variables. So if we go back to our cricket data, we made the scatter plot, we could get a sense for that positive trend to it. And what we couldn't calculate, though, is we can't calculate R. Well, we can, but we're just not going to. Instead, I'm going to give you R. So for that cricket data, we're being told that correlation, so that's what we're being told here, the correlation is 0.8135. So what we can do is see where are we landing on that number line with the 0.8135. So we are going to be out here. There's our 0.8135. So with that, we get two pieces of information. You can see the linear relationship is strong and it's going in a positive direction, which again, the direction we can usually see from the graph itself, but the strength is a little more difficult. So what we could say is the association between temperature and chirps per second is positive and strong. So this question of describing association, always describe direction and strength. So you're using R to get out the two characteristics there. Do these results confirm that the increase in temperature leads to a higher number of chirps from crickets? Now that leads to is just a little too strong a wording. That's suggesting cause and effect. If one thing happens, it leads to another, which we still don't have here, and we just will never have, no matter how strong the data is. I mean, the stronger the strength is, it starts really suggesting that there is something going on, but there still could be lurking variables. So with this, no, because we can't claim cause and effect. But we could say we see a strong association. But again, it has to be that looser wording. All right, the last piece I want to talk about in this video is the coefficient of determination, which is looking at the value for R squared. So R squared is literally the square of our R value. And what it tells you is this kind of percent variability. So our units, when you get R squared out, it is a percentage. Just remember though, R is not a percentage. So when we get out our correlation value, that is not a percentage, it's just a spot on the number line. But when we square it, it turns into a percentage that we can evaluate. So just be really careful of that, because if you give me R as a percentage, I would take off points for that because it's not correct units. So our coefficient of determination tells us the percentage of the variation in the Y values that can be explained by the regression line, which we talk about the regression line more in a following video. But how we could relate this now for another interpretation is it tells us the percent of variation in Y that can be explained by X. So it's another way of describing the relationship between the two variables. So let's look at an interpretation using the crickets data. So we had R equals 0.8135. So calculating R squared, we would just take 0.8135 and square it, and that would give a 0.6618. So remember, X is temperature and Y is chirps per second. So how I could interpret this is 66.18% of the variability in chirps per second can be explained by temperature. So it's a way of describing the relationship, as you can kind of get the sense of the higher the percentages, the stronger that association is going to be. So in this case, chirps per second varies in some way. Just cricket to cricket, time of day to time of day. There's some variability. And what we can determine from this relationship is 66.18% of that variability is coming from temperature. So say this had actually calculated to 100%. That would mean how chirps per second changes completely relies on temperature. Then as this percentage decreases, like say that only said 5% of the variability, it's like, okay, chirps per second changes a lot and barely any of it can be explained by temperature. So it's just a way of kind of working with the strength of the data, but with an interpretation we can more easily understand. So with coefficient of determination, square R, change it into a percentage, and then you can kind of fit this sentence form here of have your percentage, you're describing the variability, and then it's your variability in your y variable, and then it can be explained by your x variable.